Good afternoon, and welcome to our humble class again. Thank you for tuning in. I hope that this is going well for everybody. Um, I haven't heard anything to the opposite yet, so let me know if things can be improved upon. But a number of you have been contacting me and asking questions, and that's always a good thing. So you have my telephone number, area code 562-760-3569, if you have questions or if you want to text. But today we're going to be talking about some of my favorite things. I got my PhD in a field called ring theory, and we're going to talk a little bit about rings today. So let's pray and let's talk about one of my favorite things. Father, thank you so much. Talking about you is my favorite thing. Thank you, Father, for the fact that you love us so much that you want to spend time with us. You want to be with us whenever there are two or three of us gathered in your name. And Father, we don't have to be in the same room to be gathered in your name. We can be gathered here on the internet and glorifying you by studying the things that you've created. Thank you for your creativity and your artwork and putting together things that we can study and enjoy. And I pray, Father, again, that you give us wisdom, collectively speaking and individually, so that we can understand and so that I can be clear and students can get it. In Jesus' name, amen. Okay. Very simply, a ring is any non-empty set where you can add, subtract, multiply, and the multiplication may or may not be commutative. Now, you're familiar with the fact, you've been familiar with this since grade school, that 3 times 4 is the same number as 4 times 3. That's the commutative law of multiplication. But there are plenty of rings in which that's not true. Those are called non-commutative rings. So let's define what a ring is, and we'll be off and running. Definition. A non-empty set are supplied with 2 operations called addition and multiplication, which a lot of times we just write with a dot between elements, is a ring if the following things are true. If R is closed under these operations, so in other words, A and B being elements of R implies that A plus B is an element of R, and A times B is an element of R. So when you do, that's the first of the requirements. If you do these operations for elements that are in the ring, you don't go flying outside the ring by doing that operation. So that's actually the zeroth property. It has to be closed under those operations for any of the following things to make sense. But property 1, A plus B equals B plus A, for all A and B in the ring. In other words, addition is commutative. Commutative law of addition. Number 2, it's associative. A plus the quantity B plus C is the same as the quantity A plus B plus C. Once again, that's for all A, B, and this time C in the ring. The associative law. Property 3. A times B times C, A times the quantity B times C, is the same as the quantity A times B and then times C, once again, for all A, B, C, and R. And I don't need to write down the associative, the word associative again. This is the associative law of multiplication. 4. The multiplication and the addition have to talk to each other in a sense. If I take A times the quantity B plus C, then this is A times B plus A times C. That is a distributive law. And it's distributive on the other side too. If I take the sum first, A plus B, that quantity times C, that's equal to A times C plus B times C. And again, a distributive law. Number 5. There exists an element 0 such that A plus 0 equals 0 plus A equals A for every element A in the ring. And you're very familiar with 0. And 6, there exists an additive inverse. We're going to call it minus A, such that A plus this thing, A plus minus A, is equal to 0. And once again, that's for every element A in the ring. If a non-empty set satisfies those properties, that non-empty set is referred to as a ring. The classic example of a ring is a set of all integers. If you take the set of all integers, certainly addition is commutative and associative. There's a multiplication, it's associative. The distributive law, both of these work, but actually with the integers, because multiplication is also commutative. Notice that I didn't put the commutative law of multiplication in here because not all rings are commutative rings. Commutativity meaning the multiplication. Addition is always commutative, always, always, always. But multiplication, maybe yes, maybe no. With the integers, multiplication is commutative. And so I don't need both of these laws, because with a commutative law, I could just take this and move it across A, and I get the second law. So the classic, and of course we have a 0 in the integers. Everything has a negative for the integers. And so the, the classic example for the case of a ring is the set of integers, and it is a commutative ring. It also has a very special property called unity. If there exists a 1 in R such that A times 1 equals 1 times A equals A for all A in R, then R is called a ring with 1. Big surprise. If A times B equals B times A for all A and B in R, then R is a commutative ring. If A times B equals 0 implies that A equals 0 or B equals 0, R is a domain. Okay, now let me talk a little bit about these, because you would think, well, of course, that's obvious. If you had two things that were not 0 and you multiply them together, you can't possibly get 0. Well, that's not always true. We're going to be discussing in a few minutes, for example, the idea of a matrix. It's possible to have a non-zero matrix multiplied by a non-zero matrix, and lo and behold, you get 0 as the result. We're going to show you that example in a few minutes. So this becomes an important property. Any time that you have two elements multiplied together that give you 0, both of those elements are so-called zero divisors. They're divisors of 0 because you multiply them together and you get 0. But when you do not have any non-zero zero divisors, the ring is called a domain. A domain with 1 is called an integral domain. Question: what about the integers? Do the integers form an integral domain? Well, first of all, they have a 1, so that takes care of the integral part. Are they a domain? If you take two non-zero things, when you multiply them together, is it possible to get 0? You don't have to think about that very long to realize, no, you can't possibly do that. So the integers do form a commutative ring. They're also a domain, and they have a 1. So they're at the top of the food chain so far. But the food chain goes a little farther. If for every non-zero element of the ring, so non-zero A in R, there exists an element, say Q in R, such that A times Q equals Q times A equals 1, then if R is an integral domain as well, and meaning that it's commutative, it has a 1, doesn't have zero divisors. Well, this law is stronger than not having zero divisors. Everything actually has an inverse. So R is now called a field. So there is indeed a hierarchy here. And in fact, we're not going to deal with any rings that fail to have the associative law of multiplication, which is this law here. But there are so-called rings that are non-associative rings. We're not going to be interested in that. It's pretty high-powered stuff. If you go on in mathematics, you might study non-associative rings in graduate school. You might not, depending on what area you plan to go into in mathematics. Mathematics, like every other field, has become extremely, did I say extremely? Yeah, extremely focused, diversified. You can go into mathematics and you can go into analysis, which means you study calculus, and then you study functional analysis and measure theory, and you study not only the Riemann integrals that you get in calculus that you get in your freshman and sophomore year, but you can study Lebesgue integrals. You can study all sorts of fancier functions on different kinds of sets. You can study topology, which has to do with continuous functions on any kind of sets, not just on the real numbers or the rational numbers, but on the set of all yucca plants in New Mexico. As long as you have some kind of a structure where functions can be called continuous, then you have the whole field of topology. You can combine calculus and topology and study what's called differential geometry. You can combine calculus with algebra, and then you'll have algebraic topology. That just goes on and on and on. The combinations, and when you take these different fields of study, and you push them and push them and push them until you finally see the other side of things, all of a sudden the beauty of God's artwork becomes magnificent, because you see how all of these things join back together on the other side. These fields connect together. When you take linear algebra and you study vector spaces and linear transformations, you can combine them with topology and talk about topological vector spaces. And you can combine algebra and talk about group theory and talk about topology, and you get topological groups, and you can talk about topological rings, topological fields, topological vector spaces. And then you press that a little bit farther, and it combines with analysis, and you talk about functional analysis. The beauty of God's mathematical creation is just beginning to open up for you. And if you can continue to study math, and you continue to open up these avenues, I just hope that many of you will get to the other side where you start to see these things joining again, and see how creative God was when he put together our mathematical universe as well. Fields are kind of a basis for many of those topics. For example, linear algebra. Those of you who go on to study vectors and vector spaces will find out that at the core of these vector spaces are fields. There are many fields that you're familiar with. For example, you're familiar with the real numbers. Well, the real numbers have all these properties. You can add. Addition is commutative. Addition is associative. Multiplication is associative. Multiplication is commutative. If you multiply two things that are non-zero together, you can't possibly get zero. So it's an integral domain. It has a 1 in it. You're familiar with the real numbers having a 1 in it. But every non-zero element also has an inverse. So the real numbers form a field. But also the rational numbers form a field. You take if you take the rational number p over q, and p is not 0, and of course q is not 0 either, then it's, when you invert it, q over p, that turns out to be the multiplicative inverse, so q is a field. The set of irrationals is not. In fact, the irrationals are not even closed under addition. If I take the irrational number, the square root of 2, and I add it to the irrational number, negative square root of 2, I get a rational number, 0, so they're not even closed under addition. They're not closed under multiplication. The square root of 2 times the square root of 2 is 2. That's a rational number. So the irrationals aren't any of these things, not even a ring. But the complex numbers, those are a very special field, because in the complex numbers, they're what is called algebraically closed. And we're going to be talking about that property in the future, but let me just drop the hint now. What it means is, if I have a polynomial whose coefficients live in the complex numbers, and I set that polynomial equal to 0, if it's a polynomial of degree n, then all n of the roots of that polynomial actually live in the complex numbers. Well, that's not true in the real numbers. It's certainly not true in the rational numbers. If I take the rational polynomial 3x plus 2 equals 0, you get a solution in the rational numbers for that. Fine. But if I take the equation x squared minus 2 equals 0, the coefficients are in the rationals. In fact, they're integers. But the solutions of x squared minus 2 equals 0 are not rational numbers. They're plus and minus the square root of 2. We proved earlier in the semester that the square root of 2, if it exists, and we'll get into that a little bit later in the semester, but the square root of 2 cannot be a rational number. And that was an easy proof. We did it by contradiction, you may recall. So it's possible to have equations with coefficients in the rational numbers, in fact, coefficients in the integers, where the solutions to that polynomial equaling 0 do not live in the rational numbers. As a matter of fact, they might not even live in the real numbers. Suppose I take the equation x squared plus 1 equals 0. To satisfy that equation, x would have to be the square root of negative 1. And they've told us ever since we were in junior high school, there is no square root of negative 1. Well, this is another example of what I told you. Sometimes nice people lie. They're not lying because they want to deceive you. They're lying because they don't want to overwhelm you. But a lie is a lie. There is a square root of negative 1. And you can actually use ring theory to develop it, to show where it comes from. Maybe if you're good girls and boys, I may actually show you that procedure. But if you ask, I can do it on an individual basis. It's a little complicated, but I think I could help you to understand it. So there is a square root of negative 1. The equation x squared plus 1 equals 0 does have solutions. Those solutions, though, are not real numbers. They are what's known as I and minus I, plus and minus the square root of negative 1. It's unfortunate that those are not called real numbers, because the set of real numbers, we're familiar with what those are: positives, negatives, zeros. Rational and irrational numbers make up the real numbers. But the complex numbers, numbers that include I or negative I, those numbers don't fail to exist. So to call them not real just kind of irks me. To call I imaginary, which is what the I stands for, that kind of irks me too, because it's not imaginary. Not only can I imagine it, I can construct it. So it really does exist. So we're going to talk a little bit about the complex numbers and the so-called imaginary numbers I and negative I. But a field is a place where you can add, subtract, multiply commutatively, and divide by anything except zero. That's a field. And what I want to do next is I want to examine the properties of a field. And let's just go ahead and start chipping away at it. I guess I'm going to have to do some erasing. It's time for me to do some work. Turns out that erasing a board doesn't always just have to do with getting rid of the black on it, but also getting rid of the wet on it. Let's take a look at the rational numbers. The rational numbers are defined by the quotients of integers. So where P and Q are integers and Q is not zero, you can't divide by zero. Now when you take calculus, you can kind of stretch that a little bit with what's called L'Hopital's rule. It's not really division by zero, but it kind of takes care of similar situations where you have zero in the numerator and in the denominator. But for right now, you never have zero in the denominator. That's a set of rational numbers. Q is also the set of all let's call them, I debated a little bit, repeating decimals. Let me talk a little bit about that. You've probably been told earlier in your life it's a set of all either repeating or terminating decimals. Well, a terminating decimal is one where eventually you get nothing but zeros. So for example, 1 over 4. 1 over 4 is obviously a rational number. 1 over 4 is obviously a repeating decimal. It's also a terminating decimal because 1 over 4 is 0.2500000, but that qualifies as a repeating decimal because 0 repeats for a very long time. So I don't use the phrase terminating decimals. I just use the phrase repeating decimals because all terminating decimals do repeat. They repeat with zeros. Okay? The fact that these two are characterizations of the same set, the set of rational numbers, you should be able to move from one to another back and forth without any difficulty. And indeed you can. To show that this is if and only if, it's possible to prove it. I'm not going to bother to prove it because that's really not where we're going in this course, but I want to show you how to do it. For example, how do you get from 2/7 to a repeating decimal? And the answer is 2 over 7 means it's division. So divide. Now you need to carry this a little bit farther. So put in a point and a 0. What do you multiply by 7 to give you 20? Well, the biggest thing that you can put in there is a 2. 2 times 7 is 14. Subtract, you get 6. Bring out the next 0. And what times 7 would give you 60? And the answer is 8. 8 times 7 is 56. 4, bring down the next 0. What times 7 would give you 40? And the answer is 5. 5 times 7 is 35. Subtract, you get 50. Bring down the next 0. What times 7 gives you 50? And the answer is 7. 7 times 7 is 49. Difference is 1. Bring down the next 0. And then you get a 1. 1 times 7, 7. Bring down the next 0. What times 7 gives you 30? The answer is 4. 4 times 7 is 28. The difference is 2. Bring down the next 0. And now we're back where we started again. So these 6 digits repeat. So 2/7 is exactly equal to 0.285714285714285714 on forevermore, amen. So you can always do that. You can always turn a fraction of integers into a repeating decimal. Can you turn a repeating decimal into a fraction? Well, let's do a simple one. Suppose I take 2.431 repeating, and I want to turn this into a fraction. Well, you'll notice that there are 3 digits that repeat. What this notation means is 2.431, 431, 431, 4, et cetera, et cetera. And so if I multiply this by 1,000, which is 10 to the 3, then 2.431 times 1,000 is equal to, well, when you multiply by a power of 10, you shift the decimal, that number of places, in this case to the right. So that's 2,431.431431. So if I let x be 2.431 repeating forever, now that I've multiplied that by 1,000, I've got 1,000x is equal to 2431.431 forever. And if I subtract, let's subtract it in the other order, 1,000x minus x is 999x. 2431 point tail minus 2 point tail is 2429, and the tails cancel each other. So x is equal to 2429 divided by 999. And so I've turned this repeating decimal into a fraction. You can always do that. So fractions into repeating decimals, always. Repeating decimals into fractions, always. And that's the process. Now, let's do a little more erasing, and let's talk about the rational numbers a little further. Okay. A lot of times people describe mathematics as the subject of solving equations. by now you're probably beginning to understand that that's not even close to a complete description of mathematics. Mathematics is an artwork of God that has to do with much, much more than solving equations. It has to do with structures and surfaces and all sorts of different things. But solving equations is hugely important in mathematics. And as I mentioned before, there are times when, especially with a field that is as limited as the rational numbers, there are not a lot of equations that can be solved within the rational numbers. You can solve ax plus b equals 0. Fine, x equals minus b over a. That's not a terribly complicated equation. And that solution is a rational number if a and b are both integers. In fact, if a and b are both rationals. But, as I mentioned before, the square root of 2, the square root of 3, the square root of 19, the square root of 141, 142, and numbers like that, those are not rational numbers. So what if I started with the rationals and I said, yeah, but I'd like to be able to solve this equation in the rationals. Well, you can't do it maybe in the rationals, but you can extend the rational numbers to include such a solution. For example, we already mentioned and we proved in class that the square root of 2 is not a rational number. But consider the set a plus b times the square root of 2, where a and b do live in the rational numbers. Okay? Now, if b is not 0, this is not a rational number. But what I've done is I've kind of extended the rational numbers. I call q square brackets square root of 2 to be the set of all a plus b root 2, such that a and b live in the rationals. This is indeed an extension of q because q lives in here. If b is not 0, I just get rational numbers. But now I get more numbers than I had before. We've talked a little bit about different sizes of infinity. When I attach the square root of 2 to q in the way that you've just seen, as it turns out, I don't get a bigger infinity. Now, you might remember what I mean by this. If not, I'm going to freak you out again. The set of real numbers is infinite, as the set of rational numbers is infinite. However, the set of rational numbers can be put into one-to-one correspondence with the set of integers. In fact, the set of counting numbers, 1, 2, 3, 4, 5, the natural numbers. And it's done by a clever diagonalization process. You can look up Georg Cantor on Wikipedia if you want to see that diagonalization process. It's not difficult. In fact, we talked about it a little bit when I showed you ordered pairs of integers, and as we talked about those lattice points and all. But when I adjoin the square root of 2 to q, I don't get a larger infinity. It's still in one-to-one correspondence with the natural numbers. But when we pass to the real numbers, we actually get a larger infinity. Okay? It's called uncountably infinite, whereas the number of elements in here is countably infinite. Remember that doesn't mean that you can count it. Countable does not mean able to be counted. We're going to be talking about this in depth in a couple of weeks probably. But the punchline to this is that countable just means it's in one-to-one correspondence with the counting numbers. You're not able to count it in a finite number of times. Now, if you want to devote your time in heaven to doing that, have fun. There will be much more fun things to do in heaven than that. But, whatever floats your boat. But the real numbers are uncountably infinite. They're just a huge infinity. And we talked about the fact that the number of subsets of real numbers is an even bigger infinity, and the infinities keep going on bigger and bigger, and finally we decided that there is an infinite number of different sizes of infinities. But here I get what is called a two-dimensional vector space over Q. We're not going to talk about vector spaces this semester. When you take linear algebra, I'm sure your professor will be happy that we didn't talk about vector spaces this semester, because I'm sure that's something that he would like very much to propose to you for the first time. But it turns out that if you have a set where you're adjoining to Q the solution to a polynomial equation of some finite degree, like x squared minus 2 equals 0, solution being plus and minus the square root of 2, well, you still get the same size of infinity. Now, what is in here? And what kind of a thing is this? Is this a ring? Is this a field? What kind of a beastie is this thing? Well, we can define addition and multiplication in the obvious ways. If I have 3 plus 2 root 2, and I add that to 1 minus 4 root 2, then what I do is I take the rational parts first, that's 3 plus 1, and then I take the irrational parts, that's plus 2 minus 4 times root 2, and I get 4 minus 2 root 2 as the answer. So what the punchline is, it doesn't matter what rational numbers I put in here as the coefficients. When I add two of these little monsters together, I'm going to get another one of these little monsters, which means that this set is closed under addition. It's also closed under multiplication. Let's multiply these two numbers together. 3 plus 2 times the square root of 2. Let's multiply that by 1 minus 4 times the square root of 2. And you FOIL this thing, so that's 3 times 1 plus 2 times the square root of 2 minus 12 times the square root of 2 minus 8 times the square root of 2 times the square root of 2. But what's the square root of 2 times the square root of 2? It's 2. So this is 2 times negative 4 is negative 8 times 2 is negative 16. So when I add these all together, I get negative 13 minus 10 root 2. What's the punchline to that? I can multiply these little monsters together, and this set is closed under multiplication. There is a 0. 0 plus 0 root 2 is the 0 in this ring. There is a 1. 1 plus 0 root 2 is my 1. And so I have here an integral domain. Is it more than that? In fact, I haven't proved that it's a domain and that it doesn't have any zero divisors except 0. But I mentioned a little earlier that having an inverse is even stronger than being an integral domain. So let's see if everything in here has an inverse. What is 3 plus 2 root 2 divided by 1 minus 4 root 2. Can I do such a thing? And the answer is yes. I implore the muses of conjugation to give me an answer. Now, would you agree that if I multiply by 1, I haven't changed anything? Hopefully. If not, we need to go back 1 or 2 classes before this one. But if you agree that multiplying by 1 doesn't change anything, but I have this unique way of defining 1. I take the bottom number with the opposite sign. So now it's 1 plus 4 root 2 over 1 plus 4 root 2. And when I do this multiplication, up on top I get whatever I get when I FOIL. I get 3 plus 8 times 2. So 3 plus 16, I get 19. And what's the coefficient of the square root of 2? I get 2 root 2 plus 12 root 2, which is 14 root 2. But I'm dividing by the product of these two, which comes out very nicely. 1 minus 4 root 2 plus 4 root 2, and the people all said, poof! So those go away, and I'm left with minus 4 times 4, negative 16 times the square root of 2 squared, negative 32, which is negative 19 over 31 minus 14 over 31 times the square root of 2, which is another one of these BCs. So the punchline to this part is I can divide. The way that I divide in this new set is that I take the denominator, I multiply and divide by its conjugate, meaning the same thing with the opposite sign, and the result comes back being in this set. Now entertain yourself while I erase the other board. Okay. And let me take a swig of my iced tea so my throat doesn't feel like the Sahara Desert. And let's define what's called a matrix. Definition. A matrix over a ring R is a rectangular array of elements of R. Well, that was easy to say. Now, a rectangle can be of any height and width that you want. Suppose that I have a 2 by 3 rectangle. A 2 by 3 matrix has 2 rows and 3 columns. In talking about the size of a matrix, n by m, the first of the two numbers is always, 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 always the number of rows. The number of columns is 3. Now, if you have a problem with knowing what are rows and what are columns, just remember that columns support the front of the White House. Columns are vertical. The front of the White House would be in deep yogurt if it was supported by something, by things that were horizontal, right? So columns are always vertical, and that leaves rows to be horizontal. So the matrix 1, 3, 7, 2, -1, 4 is what? 2 by 3 or 3 by 2? Well, there are 2 rows, 3 columns, so it's a 2 by 3. Whereas 1, 3, 7, 2, -1, 4 is a 3 by 2 matrix. If I have 2 matrices of the same size, I can always add them. So let's make that comment. Matrices of the same, and the better word is dimension, same dimensions, m by n, say, can be added and subtracted. Okay, so if I have a 3 by 5, not the card, but the matrix, if I have a 3 by 5, I can add it to another 3 by 5, and the result would be 3 by 5. I could subtract 3 by 5 from a 3 by 5 and get a 3 by 5. And the way that you do that is you do it entry by entry, which is why they have to be the same size. So let's do an example or 2 of those after I get this other board erased. I'm very grateful for this room where I was able to put up another board and do these lectures here, because since I couldn't go back to Biola to do the lectures, the only alternative would have been, to go to a forest, write the stuff up on a tree. You can't write very much, and I have to go from tree to tree. It's hard to erase a tree, and so, this was a much better alternative. Let's take this example. If I take 3, -1, 4, 7, 2, 5, and I say subtract 1, 2, -6, 3, -2, 4, and I do this component by component, 3 minus 1 is 2 this week and this week only, right? -1 minus 2 is -3. 4 minus -6 is 10. 7 minus 3 is 4. 2 minus -2 is 4. And 5 minus 4 is 1. So the difference of these two matrices is this. The m by n matrices of any sizes m and n are closed under addition, they're closed under subtraction. Well, how about multiplication? Let's talk about multiplication a little bit. And by the way, well, I'll get there. Some, by the way, just have to wait. Do you know what I mean? Can I multiply these things? Is it conceptually possible to do the same thing with multiplication that I just did with addition? Could I take 3 times 1 is 3, negative 1 times, times 2 is negative 2. Could I take those products? The answer is, of course, I could. But what I get does me very little good. Now, there are some problems and some sizes of matrices that are useful in various fields of mathematics where that's a reasonable thing to do, the inner product and vector spaces, that type of thing. But as far as the physical representations that I get from matrix multiplication, I want more. For example, whenever you take linear algebra, you may get a homework problem that has to do with a part of physics called optics. But whether you do or not, the following is correct. Suppose that you take an optical system, a system of lenses and media through which light is going to travel, and you start off with some object on one side with a light source behind it so that it shines on that object, and then that light travels through different media. Maybe a concave lens, followed by a convex lens, followed by some water, followed by some smoke, followed by a mirror that shines it back to here, and then followed by a convex lens that, And when that image is portrayed in each one of these lenses, in that first lens it's condensed, in the next one it's expanded, and depending on how far apart they are, the image might be turned upside down. And then when it goes through water, it's not a completely pure image, so it gets changed a little bit, refracted a little bit, and then it goes through the smoke, it gets refracted a lot. Those of you who live in Southern California know about that. But then at the very end, you get some image. Maybe it's upside down and 3 times the size. How can you figure out the upside down and the 3 times the size for an image without actually doing the experiment and measuring the thing? And the answer is, each one of these lenses, each one of these media, the water, the smoke, the mirror, everything, each one of those has a matrix that represents the properties of that lens or that medium, and it's predetermined. Once you create a lens, you are stuck with what that does to an image at different distances from the light source and all. And so if I have a matrix that represents this one, and another matrix that represents this one, and a matrix that represents the water, and another matrix that represents the smoke, and another matrix that represents the mirror, then what could I do to figure out what's going to happen with the image? That it's 3 times the size and it's upside down. And the answer is, I multiply the matrices for each one of those media. So there's got to be some way of multiplying matrices so that this all pans out, so that I do indeed get 3 times the size and inverted image. So there is a multiplication of matrices that does exactly what I want it to do. And that multiplication of matrices, I need you to practice doing 2 things at once. Now, if you're the kind of person that is challenged by chewing gum and walking simultaneously, then you'll probably need a little bit more practice on this than others. Some people will get it right away, but here are the two things. You take your left hand, you don't put your right foot in, your right foot, no. You take your left hand and move it to the right, and at the same time, you take your right hand and move it down. Believe it or not, that is how you multiply matrices. So let's take a matrix. Let's take this matrix. 3, -1, 4, 7, 2, 5. And let's multiply by, now I can't multiply by this one the way it is, but what I'm going to do is, it's called, I take the transpose of this matrix, and you don't know what that is yet, maybe, but that's all right. I'm going to transpose it, which just means I'm going to take the rows and make them columns, which is the same as taking the columns and making them rows. So I'm going to multiply this by this matrix. Now notice the size. This is a 2 by 3. This is a 3 by 2. In order to multiply two matrices, these integers have to match. This 3 and this 3 have to be the same. So I have to have the same number of columns in this one as I have rows in this one. And indeed I do. Now, can I predict the size of the result? And the answer is, well, if the answer were no, would I have asked you that question? Of course I can. And the prediction is the outer numbers. So the inner numbers have to match. The outer numbers tell me the size of the result. The result is going to be a 2 by 2. So I can actually draw the parentheses in advance. And how do I do this? Well, you already know. I go like this. Now watch. 3 times 1 minus 1 times 2 minus 4 times 6. So that's 3 minus 2 is now 1, minus 24 is -23. 7 plus 4 is 11, minus 30 is -19. 9 plus 2 is 11, plus 16 is 27, and 21 minus 4 is 17, plus 20 is 37. And this is the product. If this matrix is A, and this matrix is B, and this matrix is C, then A times B equals C. And that is how you multiply matrices. We're not going to get real technical in this. You will get very technical in this subject when you take linear algebra. If you do, I highly suggest that you do take linear algebra. It is a fascinating, fascinating field. And so let's see, what else did I want to say about this? Ah, yes. Something that I promised you, and my time is not up, so I'm going to keep my promise. I told you that there are places, specifically there are rings, where you do have non-zero elements that are zero divisors. And I want to show you an example of that. If a matrix is square, all matrices are rectangular, but if it's actually square, i.e. an n by the same integer, n by n matrix, then the set of matrices is also closed under multiplication. Because if I take a 3 by 3 times a 3 by 3, the 3's inside match, the 3's outside match, I get a 3 by 3 as a result. So I input the same size as I output. That's what it means to be closed under multiplication. So the square matrices are closed under addition, subtraction, and multiplication. Now the natural question is, are they closed under division? Can I find an inverse? And the answer is sometimes. And you'll be talking about that sometimes in linear algebra as well. But for now, let's do the multiplication on a couple of very select non-zero matrices. Now, what do I mean by a non-zero matrix? I mean any matrix where they're not all zero, 0, 0, 0, 0, 0, 0, 0, 0, right? But here, 0, 1, 2, 0, 0, negative 3, 0, 0, 4. Okay? I'm going to take that matrix and I'm going to multiply by itself. When I multiply these two matrices together, and of course I know that I'm multiplying a 3 by 3 times a 3 by 3, so I'm going to get a 3 by 3, and I do that little process, 0, 0, 0, 0, 0, 0. It's no big surprise that I'm going to get zeros all the way down here. Now, how do I get row 1, column 2 of the result? I go to row 1, column 2 of the inputs. 0, 0, 0. 0, 0, 0. 0, 0, 0. Now, how do I get row 1, column 3? And the answer is I go to row 1, column 3. 0, negative 3, plus 8, which is 5. How do I get row 2, column 3? I go to row 2, column 3, and I get 0, 0, negative 12. Let's see, where was I? Right here. And finally, I get 0, 0, 16 down here. Now, I didn't get 0 as a result, but suppose that I take one more copy of this matrix now. So that's going to be 0, 1, 2, 0, 0, negative 3, 0, 0, 4 cubed. And so that's the matrix squared times another one. So here's the matrix squared, which we just computed. And I'm going to multiply by another copy of our beginning matrix. I still know I'm going to get a 3 by 3 as a result, and I go through this again. So row 1, column 1, I go to row 1, column 1, and of course I get all zeros, and all zeros, and all zeros. For row 1, column 2, I go to row 1, column 2, and again I get all zeros, and all zeros. Then I go to row 1, column 3, and I get 0, 0, 20. Now let's see, let me check something here. And here I get, for row 2, column 3, I get 0, 0, negative 48. And 0, 0, And for the last row, row 3, column 3, I get 0, 0, and this is 64. Now notice what has happened. I've shoved everything, I've gotten rid of the second row and shoved everything over to the right. Now what if I eliminated this last element? What if I took 0, 1, 2, 0, 0, negative 3, 0, 0, 0, and I multiply it by itself 3 times? Then I'm not only going to shove everything over by 1, let's do another time. So what do I get here? I get 0, 0, 0, no surprise, and no surprise all the way down the first column. This row 1, column 2, I go to row 1, column 2, I get 0, 0, 0, 0, 0, 0, and 0, 0, 0. So that's the same as it was before, but now we're going to see something a little different. Here I get 0, negative 3, 0. Here I get 0, 0, 0. And on the bottom I get zeros. Now let's multiply by one more of these. So whereas before I moved everything over into the third column, now I'm going to move everything out. Because when I multiply these two together, I get zeros in the first column. I get zeros in the second column. And I get 0, 0, 0 in the third column. And so this matrix cubed is the 0 matrix. So 0, 1, 2, 0, 0, negative 3, 0, 0, 0 cubed is the 0 matrix, which I'm going to designate by 0, a big 0 with parentheses around it. Now, what do I mean by that? This non-zero matrix had some power of it that was 0. So not only do I have 0 divisors, non-zero things that when multiplied by something else give me 0, but I have what's called a nilpotent matrix. So 0, 1, 2, 0, 0, negative 3, 0, 0, 0 is nilpotent, N-I-L-P-O-T-E-N-T. That is to say, some positive power of it is the 0 matrix. So that's the definition of nilpotent. Next time we're going to be showing another set of examples that have nilpotent elements. Until then, God bless you, stay safe, stay well, and let's keep praying for each other. Bye-bye.